So our first set of problems deals with this equation here. C equals lambda, this is lowercase lambda, times nu. This is a fundamental equation, and so it defines the relationship between the speed of light, which is a constant, and then wavelength and frequency. So wavelength times frequency always has to equal the speed of light. I've kind of, and this is going to seem kind of silly, but to me, I always write it this way, especially when I had to memorize it, because for some reason, to me, it seems like little puzzle pieces. The lowercase lambda and the nu just like fit next to each other just perfectly. So I always write it this way, and then I'll work from there, whether I'm asked to solve for frequency or wavelength. So let's do that. So the first problem deals with green light, and so different colors of light will have different wavelengths associated with that. And green happens to be at 515 nanometers. We're asked to calculate the frequency. Because the speed of light is in meters per second, you're gonna want your wavelengths when you solve these problems to always be in meters. So that's the first thing I'm gonna take care of. So I'll have 515 nanometers, and then there's 1 times 10 to the 9th nanometers in 1 meter. Nanometers will cancel with nanometers, and I get 5.15 times 10 to the negative 7 meters as my wavelength. And so I'm going to rewrite that. And we were asked to solve for frequency. So I'm going to divide each side by wavelength. So then wavelength cancels with wavelength, and then I have this relationship. The speed of light divided by wavelength will give me my frequency. So C, the speed of light, is a constant. I'm going to do 2.998 times 10 to the 8th meters per second. And I'm going to divide by this wavelength value that we just got. 5.15 times 10 to the negative 7 meters. So let's look at how our units are canceling. So meters will cancel with meters, and then we're left with 1/seconds, which is the units for frequency. You'll also see these units expressed as s to the negative 1. I mean, that's just another way of writing 1/seconds. Or as Hz, which is hertz. So we're left with the appropriate units. And then when we finish up that, we get 5.82 times 10 to the 14th, 1/seconds, which I probably would write as 5.82 times 10 to the 14th hertz when I'm reporting my final answer. Hertz is more common than 1/seconds when you're talking about frequency, but then when you use it in the equation, you got to change your hertz to 1/seconds to see how everything cancels. The last thing before we move on to the next problem, we're going to see this relationship. Because the speed of light equals wavelength times frequency, as wavelength becomes bigger, frequency becomes smaller. So these two things share an inverse relationship. So as this goes up, this goes down. And frequency also can be described as the energy. So high frequency is going to be associated with high energy. So if we had high frequency, then we're going to have really small wavelengths. So we're going to have a really, really tight wave when we have those high frequency, high energy waves, like associated with like X-rays, for instance. So these problems right here, we're going to move on to number 2, really speak to the wave nature of light. And remember, the whole theme of at least the first part of this chapter is that light has, and energy has this wave particle duality. Is it a wave or is it a particle? But this equation is definitely associated with the wave characteristics of energy and light. So we're given 100.2 megahertz, and I know we can change hertz to inverse seconds, which we eventually need to do. But before I do that, I want to deal with the mega. So I have 100.2 megahertz. Think of mega millions. It's a really big number, right? So 1 megahertz would have 1,000,000 hertz. So megahertz would cancel with megahertz. I'm going to multiply, and I get 1.002 times 10 to the 8th hertz, which I'm not going to use in that form. When I enter this frequency, I'm going to use 1/2 so I can verify the cancellation of my units. I really like this problem. Students always clown on me because I know there's not that many people that listen to the radio anymore. I have a really old car, so I actually still listen to the radio. So this always blows my mind that by knowing the number on your radio station, you can calculate because the number is associated with the frequency, the energy of the broadcast. You can calculate the wavelength that's coming into the antenna there. And let's do that then. So again, we have C equals lambda times nu. And this time we're asked to solve for wavelength. So we'll do C divided by nu, or frequency, equals lambda. C is a constant, 2.998 times 10 to the 8th meters per second. And I'm going to divide by 1.002 times 10 to the 8th, 1/seconds. And then seconds will cancel with seconds, and I'm just left with meters. And that's perfect because wavelength has units of meters. And when I divide, I get 2.992 meters. So approximately 3 meters. You think about the meter stick, right? So 3 of those. And then what does that mean? I know there's some notes that I provided on the first page defining that, but just we want to look at that real quickly. When we're talking about the wavelength, it's the distance from the top of one wave to the top of the next wave. So from here to here, this would be about 3 meters if you were listening to FM radio. Alrighty, so the next problem is about the AM radio, very similar to the previous one. So we're going to start with the 1070 kilohertz. And even though hertz is a new unit, it doesn't feel that comfortable. We can think about kilometers or kilograms. And so we know that 1 kilogram equals 1,000 grams. So we would have the same relationship with hertz. 1 kilohertz equals 1,000 hertz. So as long as we feel comfortable with the metric prefix, will be fine. So 1 kilohertz equals 1,000 hertz. I'm going to multiply those. I got 1.07 times 10 to the 6th hertz, which is my frequency. But again, when we're entering frequency into this relationship, it's better to use the units of 1/seconds to see how things are canceling. So just like in the previous problem, if we do the speed of light divided by our frequency, then we're going to get our wavelength, which is what they asked us to solve for. So the speed of light is a constant, 2.998 times 10 to the 8th meters per second. And we're dividing by 1.07 times 10 to the 6th, 1/seconds. Seconds cancel seconds, and I'm just left with meters. In this case, I got 2.80 times 10 to the 2nd meters. So around 280 meters, which just to kind of compare, because this is specific to that frequency or that energy, but not every radio is going to be 1070. So in general, AM broadcast is going to be on the magnitude of about 300 meters. And then we compare that to the FM, which is only 3 meters. So let's find that interesting.